In this lecture, we'll take a look at a few more problems that can be solved using recursion.
The next problem we'll discuss has to do with anagrams. We're going to take a look at another problem where recursion provides a very interesting solution. So we need a couple definitions first. We say that a permutation is an arrangement of things in some definite order. So if I have a collection of things, we just have an arrangement where order does matter. Now, let's say we want to list all the anagrams of a specific word. Well, what do we mean by an anagram? We're saying that we want all of the possible permutations that can be made from the letters of the word. So, for example, let's say we wanted to anagram the word cat. So the possible ways we can arrange the letters in unique orders would be cat, CTA, ATC, ACT, TCA, and TAC or TAC. And what we find is that the number of possibilities or number of ways that we can arrange those letters is the factorial of the number of letters. So how would we have a program anagram a word? Well, let's assume that the word has n letters. The way we'll do this is we'll anagram the rightmost n minus 1 letters. Then we'll rotate all n letters one place, and then we just repeat this n times, where we would then anagram the rightmost n minus 1 letters. We would rotate all the letters again, and we'll just keep doing this until we've anagrammed all of the different possible combinations. So how do we actually rotate a word, or what do we mean by rotating a word? What we're meaning here is we would shift all the letters one position to the left. And then the leftmost one, we would just rotate that back to the right of our word. So just to give an example here, if we had the word rodeo and we wanted to rotate it, we would move the R to the far right place and shift everything down one. So rodeo would become Odior, I guess. I guess that's how you would pronounce that. But we can just simply do this to rotate the words. And what we find here is if we rotate n times, it gives us a letter, well, it gives each letter a chance to begin the word. So every single letter in our word here would end up being the starting letter for every single possible combination. So then we can just anagram the remaining letters. So the idea with this is, as we mentioned before, we anagram the n-1 letters, and that means we have all the possible words that arrangements we can get with a specific starting letter. And then when we rotate it, we have a new starting letter, so we anagram the n-1 rightmost letters again, so we can get all the possible ways that start with that letter, and we just keep repeating this, so that way every single letter is the starting point at some point in our rotation. Let's do an example with the cat. So we'll process this with the word cat and see how we would actually go about anagramming this. So we would start by displaying cat, and then we want to anagram the rightmost two letters. So we're going to deal with just at. So we'll rotate at, which means we're going to display CTA. So then we'll rotate TA, and we'd find that would give us cat again. And we don't need to display cat because we've already done that. So we'll actually rotate all of cat. So that means we would move the C over to the end. So that means we would have ATC. So we'll display that. And then we will deal with the rightmost two characters. So we'll rotate TC. So that means we would get ACT or ACT. So then we would rotate CT. And that means we would get ACT again. We don't need to display that. So we'll rotate all three letters. So that means A is going to get moved over to the right. So that means we now have TCA. So we'll display that. And then we're going to anagram the two rightmost characters. So we're going to rotate CA. That means we're going to display TAC. So then we'll rotate AC. And what we would find is, well, we get TCA again. So we don't need to display that because we've already done it. So we'll rotate TCA one more time, and we would find that gives us cat because we moved the T over, and we would say that, well, we have displayed all possible combinations, so we're done. So then the next question we need to ask is, how do we actually anagram the rightmost n-1 letters? Well, we'll call ourselves, which means we can use recursion. So we're going to let our method contain a single parameter, and this parameter is going to be the size of the word, and this is going to correspond to the rightmost n characters. This means each time we call the method to itself, we're going to look at one less character, and that way we will get closer to our base case. With that said, what is our base case? Well, here it's going to be that the word contains a single letter. So once we have a one-letter word, there is just no way to rearrange a single letter. So we would just return. All right, so then what's the recursive statement? Well, what we're going to do is we'll rearrange all but the first letter of the word. Because we said before, we have this first letter be the starting point, and we can get all of the different words that start with that letter, or at least all the different ways of arranging the letters starting with that letter. So we would do all that arrangement. So then when we're done, we would rotate the word. That way the next letter would be the starting point for the next arrangement of words or strings. Here is our method for anagramming a particular string. So we pass two parameters in this case. We have the string itself and then the size. I know we said before that we could just pass the size, but we're going to include the string here as well to make things easier for us. So we have our base case right up here at the top, where if the size of our string is 1, we're just going to return it because we can't anagram that anymore. And then afterwards, we have this for loop. And this is going to take care of making sure that we rotate all the different letters in our string. Now, the recursive statement is actually done right here. This line right here. We just call anagram, we still pass our string, and we decrease our size. And what we find is we would actually display our word whenever the size is 2. Okay, because we don't want to do it when size is 1, but we do it when size is 2. So that's taken care of right here. And then the rest of this code right here, where we get the position based on the length minus size, we extract a character, which is going to be some position, and then the last line does this rearrangement. This whole part right here takes care of rotating our string. Now, I do want to take a little bit of time to explain how we do this rotation a little bit more details, because I showed you a couple lines of code and said, okay, this takes care of rotating it, but how does this actually work? Well, we're going to take advantage of the substring method. So remember what that does is it gives us a portion of the string based on our starting point and end point. So what we first want to do is take out the character that we want to rotate. So that takes care of the line where we had the s.caret in some position. So our POS is a position that we get based on the length of the string minus the size. So that tells us what character we want to take out. So we get the character at that position. And then what we're going to do is after we take out that position or take out that character, we need to close the gap. And the way we do that is we concatenate the substring from 0 to our position, and then the substring from position plus 1 to the length. So we close that gap based on wherever the position is. So we go from 0 to wherever our position is, and then we would take position plus 1 and the length, take those two substrings, and then concatenate them together. And then we just tack on the rotated character at the end of our string. And that would allow us to rotate either the entire word depending on the position or a portion of it.
We'll now just take a quick look at the implementation of our anagram method. So we have everything in one file. And what we're going to see here is this is the exact same method that we just talked about a couple slides ago. We're just now going to actually show the code, run it, so you can see that it does provide all the different ways of arranging the letters. So here in our main method, we're going to have some string which we call cat. And then we're going to call our method and pass cat and then the length of the string. So in this case, there are 3 characters. So if we take a look here, this is the exact same method that we've saw before. So if the size is 1, we don't need to print anything. We're just going to say we're done. We have our for loop here where we're going to call our anagram method for our string size minus 1. So this is where we're going to do our recursion. And then if the size is 2, we'll go ahead and print the particular characters here. And then this part right here is taking care of the rotating. As we mentioned already, that the way we're doing this is we're going to take out a specific character at the position, and then we're going to close the gap by taking substrings of those positions and then adding the character removed at the end, and then we concatenate that into our new string. So let's just go ahead and compile and run this and see that it does work. So the compiling does work. And by the way, this code should be available online as well, so you can take a look at it and try it out for yourself. So we'll go ahead and run this. So I'll pull this up here. So we see that we have cat, and then we get CTA, and then ATC, then ACT, then TCA, and then TAC. So this does in fact print all the different ways of arranging the three letters C, A, and T.
So the question is, how many anagrams are there for a word? Well, I think we mentioned this before, but we'll say it again. If the word has n letters, then that means there are going to be n factorial anagrams. And this means if we try to find the anagrams for a word that's beyond 6 letters, this is going to be a very, very large number of anagrams.